Alrighty guys, so this is the first of my record lectures for Calc 2, and hopefully we won't have to do too many of these. We'll sort of play it by ear, but this is going to be covering section 7.7. And section 2.7, let me move this, there we go, keyboard was in my way. Okay, section 7.7 is all about comparison of improper integrals and last time we talked about how to evaluate improper integrals. So remember, improper integral is, for example, something along the lines of the integral from 1 to infinity of 1 over the square root of x cubed plus 5 dx would be a good example, because we see that we have an infinity as a upper bound, and that is what makes it improper. So let's consider this example real quick. Let's say that I want to know if this integral converges or not. Well, we could try to solve it with a u substitution. And let's say I tried to solve it with a u substitution. The problem was, so try 1 u sub. Let's say I try to do this with u substitution. The problem is that I would want to let u equal x cubed plus 5, right? So I would try to do the integral 1 over the square root of u, and I'd be like, oh, we'll let u equal x cubed plus 5, and then du is equal to 2x, 3x squared dx. And that is going to be a problem, because then I end up with, when I swap that dx out for du, I end up with the integral 1 over 3x squared, the square root of u du. This right here, right, that is bad. So that's not going to work. And this is where we basically dive right into the idea of a comparison test. If I think about this problem and I kind of look at it, I notice that it's very similar to the integral from 1 to infinity of 1 over the square root of x cubed dx. And sorry, I'm trying to write on the side of my screen. It's very tiny. Right? This is try 2. Okay, so if I look at that, it's very close to the integral 1 over the cube root of, or the square root of x cubed. And why that's useful will be apparent in a minute, but let's just think about this. Can I even solve this problem, or am I going to run into the same problem as I did with the u substitution? Well, this is going to give me, this is really the integral of 1 to infinity of x to the negative 3/2. Because the 2 in the denominator is because it's a square root and we're doing a third power, dx. Can I integrate that? I definitely can. The antiderivative, remember we would add 1 to the 3/2, and we divide by it. So what I end up with is, so negative 3/2 plus 1 is negative 1/2. And then you multiply times the reciprocal or divide by that number. So I end up with negative 2 times x to the negative 1/2. And I can always take the derivative of that if I need to check my work, but I'm sure that's right. And we're also going to we'll take the infinity and we're going to call that b. So I'm going to evaluate this from 1 to b. So what do I get here? I get negative 2 over the square root of b minus negative 2 over the square root of 1, which is really just equal to negative 2 over the square root of b plus, I almost said 1, but plus 2, right? So, and then I'm almost done. We apply the limit. So take the limit as b goes to infinity of negative 2 over the square root of b plus 2. What happens? Well, if I put infinity in the denominator, negative 2 divided by infinity, it gets smaller and smaller and smaller. And so this goes to 0. And so I know that the answer is equal to 2. Okay, so that's all well and good. But the question wasn't about 1 over the square root of x cubed. The question was about 1 over the square root of x cubed plus 5, right? But we can conclude something about the original function by using this second one. So I'm going to show you something in GeoGebra real quick, rather than try to draw it myself, because I think it's nice to see a real graph. And the nice thing about using my iPad is that I can just show you this. So we have the original function, which is 1 divided by the square root of x to the third plus 5, right? That was one of our functions. That's going to be green. And then the other function was 1 divided by the square root of x to the third, right? That was our second function. Okay. And then we were integrating from 1 to infinity. So I'm just going to go ahead and place a vertical line at x equals 1 so we know where to start looking. So we only care about that region, right? That's a nice, easy way to see it. And I can zoom in and out as much as I want. So I'm going to zoom in to about there because that seems to really show you what's happening here. Notice that my blue function, the one I used, is larger than the green function. And that is true forever, right? We took the integral to infinity. If I move this graph way over, so if I zoom out and I go, even to let's go so far as 60s, as long as it might take a while, but if I keep zooming in, well, it might take forever actually. By 60, it might be impossible to see. Oh, there it is. So if I zoom in for a crazy long time, we see that even way far out, the blue function g of x is still greater than f of x. It just gets closer and closer together. So at this point, we're talking about a difference of 0.002 in their values, which is pretty crazy. How close they get together, but it is always on top of it. And it is because of that that I can make the following conclusion. So basically what I just showed you is, all right, so here's our g of x, 1 over the square root of x cubed. Beneath it, is our f of x, 1 over the square root of x cubed plus 5. We know that this region from 1 to infinity of the white one we know that that shaded area, right, is finite. And since the yellow, if I were to shade in the yellow, since the yellow shaded area, right, So again, I'm just kind of making like a legend here to make it clear. The yellow shaded area is contained within the white area. So the yellow shade area must be finite as well. Thus, we can conclude that the original problem, the integral from 1 to infinity of 1 over the square root of x cubed plus 5 dx, converges. And that is an example, well, a really direct applied example of the comparison of improper integrals, and specifically the comparison test. So there is basically an official rule that we're going to follow anytime we're doing these. So cut this off. The comparison test. Alrighty. And the comparison test tells me that if we assume f of x is positive, so yeah, assume f of x is positive, establish some comparison function g of x. And then we have two cases. So case 1, if f of x is less than or equal to g of x, and g of x, and the integral from 0 to infinity, or is that 0? That's an a. That should be an a. From a to infinity of g of x dx converges, then the integral from a to infinity of f of x dx also converges. And that's the one we just did. We found a function g of x that was greater than f of x over the whole region. And since we found that it converged, it had a finite value, since it contained f of x within its region, well, the integral of f of x within its region, we know that that integral for f of x must also converge. Another result is now going the other way. I don't know if you can hear that. They're mowing outside my house because even at home, I seem to be cursed to constantly fight lawnmower people. But anyway, if g of x is less than or equal to f of x, and the integral from a to infinity of g of x dx diverges, then the integral from a to infinity of f of x dx also diverges. All right. Now, it's really important to remember the order of these two. It's a really common mistake to get mixed up on which goes where in terms of the order. And it's kind of straightforward. So if you just think about it, the first one tells us that if, let me try to draw a picture so you can add to your notes here. The first one tells me that if I have a large, if this is finite, then the area contained within it is also finite. And that makes sense, right? And then the second one tells me that if the, whoops, that's a little too big. If I have a area and it is infinite, then the area that contains it is also infinite, which again makes sense. If the area inside is infinity, then the area that's containing it must also be infinity. So we can only, that's why these are directional. We either find a big function and shows finite and work down, or we find a smaller one shows infinite and work up. And we're going to practice this. So let's look at another example. Let's do the integral from 4 to infinity of 1 over ln of t minus 1 dt. Okay. Now, if we look at this is another one where it's a little problematic, right? If I tried to do a u substitution, let's say I tried to do a u sub. Well, if I let u equal ln of t minus 1, du is equal to 1 over t det. And so I see that I'm just going to generate more t's in there. It's going to make a u substitution rather ineffective. You could try to do integration by parts, I suppose, and that might work. Sometimes you can do something like integration by parts or something to show that they converge or diverge. But in this case, that would be way more work than I would want to do. It's going to be definitely easier to think of a comparison. So we can, so we're going to do, so this is going to be too hard. So we're going to do try 2. We're going to go ahead and we're going to make a comparison. And I'm only emphasizing the try 1 and try 2 part because when you're doing the homework in this section, you'll find out that the problems in the book, I think like half the problems in the book, it makes sense to use a comparison test, but I think the other half, there's like a solid half where it's definitely easier to solve the integral using the skills we've gone over so far. And there's nothing wrong with showing it diverges by just solving the integral. It's just sometimes a comparison test is easier. So let's see, I lost my train of thought on what I was originally doing. We tried to use substitution, didn't work, so we're gonna do a comparison. Right, okay, so observe, I wrote that 0, that O, I thought it was a 0. Observe that ln of t minus 1 is I want to make sure I'm doing this right. This is less than ln of t, right? And then that is less than just t itself. And if you're not sure about that, you could think about what's an easy example. Let's just think about like t equals 1, right? Example, t equals 1. If I plug that in here, ln of 1 minus 1 is equal to 0 minus 1, which is equal to negative 1, which is definitely less than ln of 1, which is just equal to 0, which is definitely less than just 1, right? So there's an example in case you weren't entirely sure about that order with the natural log. But the important thing is because of this relationship, and I'm going to underline it, this relationship here, we can say that that 1 over ln of t minus 1 is greater than 1 over ln of t, which is greater than 1 over t. Whenever you're doing inequalities like this, if you make everything a fraction, it switches the inequality, and it's basically because you're dividing both sides. But a really intuitive way to just like think of it right off the bat is that, like, so for another example real quick, is that if I do, let's say, so 2 is less than 3, right? So as a direct result of this, 1/2 is greater than 1/3. When I divide both sides by 2 and both sides by 3, the 2 and 3 swap sides on the inequality. Not only that, but if I have a larger number and I take 1 and I divide it into that many parts, those parts will be smaller than dividing it into the smaller number of parts. So basically the thing in red is true because of this relationship here when it comes to inequalities. And why does that matter? Remember that when I said this rule up here, right here with the gold stars, we care about finding something to compare f of x to. And so it looks like what I found is I found a function g of x that's less than or equal to f of x. And we're going to go ahead and see if that helps us. If it diverges, then we know f of x diverges. If it converges, then that won't help us, and we'll need to find a upper bound. So let's actually evaluate it. So the integral of, oh, and I guess I should stick to white since I was doing the problem in white. The integral of 1 over t from 4 to infinity is equal to the natural log of infinity minus natural log of 4, right? Because the antiderivative of 1 over t is the natural log of t. What does that equal? Well, the natural log of infinity, the natural log function looks like this. And so it goes to infinity. As we go to infinity this way, we go up infinity. It just goes really slowly is the thing. But because of that, I end up with infinity minus 4 or just infinity. So the integral from 4 to infinity of 1 over t dt diverges. So now let's put it all together, right? So since the integral from 4 to infinity, of 1 over t dt, since that integral is less than or equal to the integral from 4 to infinity of 1 over the natural log of t minus 1 dt, then how to say this? Let's do it this way, yeah. So the integral from 4 to infinity of 1 over t dt, right up here, diverges. Since this function I just underlined is less than or equal to our starting function, we can therefore say that the integral from 4 to infinity of 1 over the natural log of t minus 1 dt diverges. So basically every time you do this, you're going to find a comparison function, you establish if it converges or diverges, and then you use that to claim something about the original function. But because of that, we are done. So that is an example of the other way around. We've now done an example of showing it converges and an example of it diverging. And you might be wondering, how do I know what to compare with? Well, there's a couple. The main thing about this section, and this is the thing you're going to want to know the most, because we are going to do sequences and series sometime soon. I need to look into chapter 8, not on this test really, but we are getting there. And when we do, the comparison test is going to be a very powerful tool. It's honestly, of all the tips and tricks that we'll be teaching you in this class, that is one of the things that really that you want to like stick with and remember, because it really applies to a lot of later math classes, and it's just like really handy. So, and specifically the comparison test for power functions, and those relationships are as follows. So if I had the integral from 1 to infinity of 1 over x to the p, this converges for p greater than 1 and diverges for p less than or equal to 1. Why is that? Okay, let's think about that real quick. So this function here that I just wrote down, when p is greater than 1, what happens is that the denominator becomes like x squared, x cubed. And so when I think about plugging infinity into it, since the denominator, the antiderivative of the denominator will still be a negative exponent, because like let's say real quick that it's the integral of 1 over x squared, right? The antiderivative is going to be negative 1 over x. So we see that even after I take the antiderivative, that is still in the denominator, right? It doesn't shift up. And if I think about throwing infinity in there, 1 over infinity is going to go to 0. So that's why it converges for p greater than 1. But if p is less than or equal to 1, it's either going to be, if the p is negative, it'll flip to the top, and that's going to end up with a x in the numerator. And if I throw an x in the numerator, I'll have infinity in the numerator, so it'll go to infinity and diverge. Also, if p is equal to 1, then it becomes 1 over x, and that becomes the natural log. And as we just saw right here, right? Here was an example. This was an example where p was equal to 1. We ended up with an infinity in the natural log, which made it diverge. And so it is because of that we had this case here for it converges for p greater than 1 and diverges for p less than or equal to 1. The next one is the integral from 0 to 1 over x to the p. Converges for p less than 1 and diverges for p greater than or equal to 1. And I will show you why that one is. I feel like on a graph might be best. Let me also write the last one real quick. And the last one that's worth noting is 0 to infinity of e to the negative ax converges for a greater than 0. Yeah, that's the other one you want to know. So let's look at the second one real quick. Why does it converge when p is less than 1 and diverge for p greater than or equal to 1? So notice the one beforehand, nope, that's not what I want. The one beforehand, nope, crap, wrong button. The one beforehand was from 1 to infinity. If I look at this one, we're starting at 0 and we're ending at 1. So the one before was an improper integral. This one is not an improper integral. If I look at my graphs real quick, all right, I'm just gonna delete some old equations. And can I set, there we go. And I'm gonna create, I should be able to create a slider. See if it'll let me do it. Nice. And then I'm going to create a function. 1 divided by x to the a. And okay, so now I gotta zoom in so we can see it. Okay, let's think about this. So on the first one, right? The first one was talking about how we make it converge or diverge, and we wanted the denominator to be, we wanted the denominator to have a positive exponent. In other words, we wanted it to be like 1 over x squared or 1 over x cubed. And that was when I was going from 1 to infinity. So, you know, from what I've shown here, 1 to infinity, because you can imagine it keep going to the right. And that was if I made it so I can make it like, you know, like there's 1 over x to the 5th. That converged because we see that as I move this to the right, I get closer and closer. I like cinch up with the x-axis, and that makes that region become more and more finite. We see how it gets really tight, and so that's why it converges. But if I am less than 1, then it switches to it becomes like, so x to the negative 1, 1 over x to negative 1 is the same as x, and we see how as it goes the other direction, it becomes unbounded, right? This orange line is going to go on forever, so we get an infinite area between. So that was from 1 to infinity. But the second rule is talking about specifically from 0 to 1. And it might be, let me just see. I'm just going to put some vertical lines in here so that way you can see the area I'm trying to emphasize when I talk about this. 0, x equals 1. Okay, so we care about what's happening between the gray and blue line for this one. This one, it switches. This one, the area is going to be finite if a is negative, so it becomes, see that? Notice how, as I move to the left here, after 1, it becomes an unbounded area, which is why from 1 to infinity it diverged. But from 0 to 1, we see that it cinches up to the x-axis there. So we see how it approaches a finite value as that goes in the negative direction. But then if again, we're looking from 0 to 1, if I move in the opposite direction, sure, it converges after x equals 1. We see how over there it's converging. But what's happening between 0 and 1? I start to diverge, right? I get this asymptote. Notice how that's an infinite area. If I keep scrolling up, there's always going to be more area there. And yeah, it is getting smaller, but the idea is it's not getting small fast enough. So it ends up diverging. And hopefully that makes sense. So that's why these two rules work. So how do we know what to compare with? Ideally, if f of x is if f of x can be compared to x to the p or e to the negative ax, use the following. And I'm going to leave it to you to see why this one works if you want to. But if you think about e to the x goes to infinity. It's an increasing function. If I make it negative, it reflects over the y-axis. It switches direction. So it goes from going to this way to going, this is e to the ax. E to the negative ax is this right one. So we see how the right one, I have a finite area here. So that's why e to the negative ax is useful. Anyway, but you can like play around with that on GeoGebra if you're curious. So those are our main ones we're going to use. Those are our best choices. And with that being said, it looks like, let's see, I started at 12:30, so I have about 13 minutes. So I will do a handful of examples, and we will call this lesson complete. So one of the first ones I should do is some type of, well, let me do some of the trickier ones first. So let's say I have something with a trig function, because I like this example. I have the integral from 1 to infinity of sine of x plus 3 over the square root of x dx. Now, this is one of the trickier ones. So I gave you some ones to look for if they look like a power function or e to the x. This one is a trig one. It does not match the three styles I just presented here. And so for this one, we have to think a little outside of the box. What I can do for this one is we can note that sine of x always fluctuates between 1 and negative 1. And because of that, we know that this function here, right, this is my f of x, we know that it has to be between negative 1 plus 3 over the square root of x, has to be a lower bound for f of x, which is sine of x plus 3 over the square root of x, and that has to be bounded above by 1 plus 3 over the square root of x. In other words, negative 1 plus 3 is 2, so 2 over the square root of x and 4 over the square root of x bound f of x. And so if we think about our comparison test, right, we have two choices. Let me find it up here. We can either check the lower bound and see if it diverges, or we can check the upper bound and see if it converges. Now, for the sake of time, I am going to start with the lower bound immediately rather than doing the upper. Generally, when I'm dealing with sine or something, usually a lot of trig functions like this diverge anyway, so I kind of like instinctively guess to do the first one right away. I think in the book they show you that you should do both, and I will show you a graph in a second of what's happening there, but I'm just going to do the left one, because remember, if we can show that the left one, if this diverges, we are done by comparison test, right? So let's just look at it real quick. If I take the integral and I'm using the same bounds, 1 to infinity of 2 over the square root of x dx, what is this equal to? This is the integral from 1 to infinity of, so rewrite this in a way that's a little easier to see. That's x to the negative 1/2, right, if I rewrote it. So if I add 1, that's going to be 1/2, divide by it, I'll multiply it by the reciprocal, so I end up with 4x to the positive 1/2. You can always take the derivative to make sure if you're not sure that you did it right. And whoops, and that's not an integral anymore because we just took the antiderivative, so now I need to replace that, 1 to infinity. So what does I get me? I get 4 times the square root of infinity minus 4 times the square root of 1. What does that equal? Well, infinity times 4 is infinity, minus 4 is infinity. Diverges. I'm going to call this g of x. Since g of x is less than or equal to f of x, we can say that the integral from 1 to infinity of f of x dx, which if you're going to write it like this on a homework or on a quiz, I'm allowed to cheat and just write it this way because I already earlier specified that f of x was that function. If you're going to use shorthand notation in saying if something converges or diverges, you need to make sure it is labeled. I'm not just going to assume that I know what you mean. So since the g of x is less than or equal to f of x and g of x diverges, and g of x diverges, we know that the integral from 1 to infinity of f of x also diverges by the comparison test. I know that it might seem silly that I'm saying by the comparison test, since that's the only test we're doing right now. But again, at some point, we're going to have other tests to learn about functions. And so it is important to, man, I'm getting tired today. It is important to be explicit when you're talking about what test you're using. All right. So that was a tricky one. That was a sine one. Let's do one that's a little less tricky. All right. Let's do another example. Okay, let's say I have, and I'm going to make this one up because it looks like I forgot to write down a polynomial one. Let's say I'm taking the integral from, I don't know, we'll do like 1 to infinity of 1 to infinity of x cubed over x to the 5th plus x plus 1, right? That'll work. Now, again, we have these 3 handy integral rules that I want you to think about. You kind of want to always be thinking about how can I compare whatever I'm doing to one of these 3. Obviously, it doesn't always work, but it's worth considering because these are really nice and easy. Now, you'll notice all these have 1 in top and x to the p in the bottom, and it might be like, well, this looks nothing like one of these. Here is where we want to kind of break this down a bit. This is going to be equal to the integral of, or not equal to. So note that x cubed over x to the 5th plus x plus 1, right? That is necessarily less than or equal to x cubed over x to the 5th, right? If I add more parts to the denominator, it makes the overall fraction smaller. So this is equal to this, or less than or equal to this, which is equal to 1 over x. Oops, I almost made it negative squared, right? So then I can factor out the x cubes. So I have an inequality that is in one of my handy 1 over x to the p forms. Now, from my handy forms up there, I know that, note that here, so this is where specifically p is greater than 1. So if I look up here at my 3 rules, where'd they go? That's too far. What am I doing? I am doing the first case, right? I'm doing this first case here. And p is greater than 1. So I already know that it converges by one of my rules. Now, it is important to show why that is. You don't want to rely on memorizing these because it's really easy to memorize, to forget the inequalities on a test or quiz. But let's just verify that it is going to work the way this says it is. If we go down here, okay, if I take the integral from, I'm going to do a different color for this. If I take the integral of 1 to infinity of 1 over x squared, or x to the negative 2 dx, what does that get me? So we add 1 to the exponent, making it negative 1, divide. I end up with negative x to the negative 1, evaluated from 1 to infinity What does that give me? It gets me negative 1 over infinity minus, oh, and I meant to write it as a limit. I'm almost out of time, so I'm not going to fix it. I'm being lazy. We should always rewrite this infinity as a b and then apply the limit, especially because we might need to do L'Hopital's rule or something at some point, and anytime we start doing that, we want to be precise in our notation. We're almost out of time, so I'm going to let it slide right here, and you're following along anyway, so you get what I'm saying. This is important. We're just not going to do it right now. Do as I say, not as I do. So negative 1 over infinity minus a negative 1 over 1. What does that end up equaling? Well, when we apply the limit, that is going to go to 0. And so I'm going to have positive 1. So it converges. And so then I can say, since, and I'm going to label things, since this is, so the gold one, this is g of x, and the white one, this is my f of x. Since g of x is greater than or equal to f of x, and g of x converges, and g of x converges, the integral from 1 to infinity of x cubed over x to the 5th plus x plus 1 dx also converges by the comparison test. All right, that's 120. So I'm technically out of time. Yeah, I'm technically out of time. I do want to say one other thing. I'll make this fast. This is an example where sometimes it's better to just solve it. If I wanted to ask you to find me the integral from 4 to 6 of 1 over the square root of t minus 4 dt, you may want to try using a comparison test. But the problem is, let's say you want to compare 1 over this is going to be, I'm trying to do this in a hurry. I'm going to make mistakes if I do this in a hurry, so I should slow down. Note that 1 over the square root of t minus 4 is very close to 1 over the square root of t. But the problem is that 1 over the square root of t minus 4 is in fact greater than, right, because we're minusing, not adding, so the denominator is getting smaller, making the thing bigger, is in fact greater than 1 over the square root of t. And this is basically in the form 1 over t to the 1/2, which we're doing a finite range, so it'll work. So this will converge when you try to integrate it, but the problem is it's a lower bound, and convergence doesn't tell us anything for the upper bound, right? We always want to go, if this diverged, that'd be useful, but it doesn't. But this is an example where you get so focused on comparison, you miss the easier picture. Before we talked about comparisons, if I asked you to solve this, one of your first instincts might have been to be like, oh, well, this is just the square root, 1 over the square root of u du, where u is equal to t minus 4 and du is equal to dt. And then I need to change my bounds. And then you could actually solve this just using regular integration. And you'll be able to find the answer directly. So here's an example where the direct approach is better than the comparison test. And if you go ahead and solve that, you should find that it converges. And I'm out of time, so I'm not going to do it, but it converges. Because u to the negative 1/2, you would then take the antiderivative, making it u to the 1/2. And so you'll have a square root of x type function. When you plug in 6 and 4 into that square root function, you get real numbers as an answer, so you're going to get a real solution. So it converges. But I can find that without ever doing the comparison test. So the comparison test is not always necessary. If you can solve it by brute force integration techniques, there's nothing wrong with doing that. And then if anything, it might make you better at doing integrating. So never be afraid to just try to do it the brute force method first. Anyway, this was our lecture. You can assume that there will be another one of these for Monday's class unless you hear from me otherwise. And hopefully I will know by the end of the weekend.